You ever stop and think about what's actually holding the world together? I mean, at the tiniest, most fundamental level? Well, it turns out it's basically a constant, invisible tug of war. And today, we're going to get a ringside seat to that fight.
So, let's start with a little mystery. You've got these molecules, right? And most of the time, they're just floating around, totally random. But then, you hit them with an electric field, and bam! They all snap into line. How does that even work?
Okay, look at this. On the left, hydrogen fluoride molecules are just a chaotic mess. Then you flip the switch, turn on the field, and suddenly they're all pointing in the exact same direction, just like a bunch of little compasses all finding north at once.
So why do they do that? It's because inside every single one of those molecules, the atoms are locked in this epic tug of war over their electrons. And here's the kicker. It's not always a fair fight.
See, when one atom is just a little bit greedier and pulls those shared electrons closer to itself, you get what we call a polar covalent bond. They're still sharing, sure, but it's a seriously lopsided deal.
And this unequal sharing, it gives the molecule a kind of split personality. The end that's hogging the electrons becomes a little bit negative. That's what that little delta minus sign means. And the other end becomes a little bit positive. You've basically just made a tiny, tiny magnet, a dipole.
Which brings us to the most important question, right? How can you look at any two atoms and know, for sure, who's going to win this tug of war?
Well, the answer comes from an absolute giant of chemistry, Linus Pauling. He came up with a genius way to actually put a number on this atomic greed, and yeah, it was so important he won a Nobel Prize for it.
And he called it electronegativity. The easiest way to think about it is like a power ranking. It's a score for how badly an atom wants to pull electrons toward itself in a chemical bond. Higher number, stronger pull. Simple as that.
So, in this atomic championship, who's the heavyweight? Who's the undisputed king of electron greed?
Meet fluorine. It gets the highest score possible on Pauling's scale, a perfect 4.0. Nobody pulls harder. Okay, so what about the other end of the scale? Who's the most generous atom? The one that barely even tries to pull?
That would be cesium. It clocks in at just 0.7. It's so weak, we actually call it one of the most electropositive elements. It's way more likely to just give an electron away than fight for it.
And here's where it gets really cool. Because we have these scores, we don't have to guess anymore. We can actually use them to predict what kind of bond is going to form between any two atoms.
And the process is so easy. It's just two steps. First, you find the score for each atom. Then, you just find the difference between them. We call that the delta En.
All right, let's do a quick example. Let's run the numbers on hydrogen chloride.
So, first up, chlorine. It's a real powerhouse. Comes in with a score of 3.0.
In hydrogen, it holds its own with a respectable 2.1.
So you just subtract the smaller one from the bigger one.
And the difference is 0.9. Okay, great. So what in the world does 0.9 actually tell us?
This chart right here is our decoder ring. A difference of 0.9, that falls smack in the middle range. It tells us the bond is polar covalent. Chlorine wins the tug of war, for sure, but hydrogen is still holding on. It's not a complete takeover.
And this is a really huge idea to grasp. Chemical bonding isn't just one thing or the other. It's not a simple choice between sharing electrons or stealing them. It's not black and white at all. It's really a spectrum, a sliding scale. On one end, you've got perfect, equal sharing. That's nonpolar. All the way on the other end, one atom completely rips the electron away from the other. That's ionic. And all that space in between, that's the huge, incredibly important world of polar bonds.
So let's wrap this up. What's the bottom line? Electronegativity. It's just a number that tells you how strong an atom's pull is. The difference between those numbers tells you what kind of bond you get. And those polar bonds, the ones that create tiny magnets, that's the secret sauce. It's why water is wet, why it dissolves stuff, and pretty much why life on Earth is even possible.
It's just wild to think that this tiny, invisible tug of war is behind almost everything we see and touch, from the way our own DNA is held together to the shape of a single snowflake. It just makes you wonder, what other huge secrets about how the universe works are hiding right in front of us, just waiting for us to find a way to measure them?